The history of the greenhouse effect goes back to the 1880s when radiation, light was being investigated. It was found that it was prismatic. You shine it through a prism, you get all of these wavelengths of light. They were doing all sorts of interesting things back then. And one of the premier chemists of the day, Selwyn Arrhenius, author of the famous Arrhenius equation, was speculating that because CO2 was known to absorb radiation, that it could possibly be affecting the heating of the Earth's atmosphere. And it was known at that time that CO2 was being put into the atmosphere by measurements from the earlier days of around the 1800s. So by 1880 they were getting different values of CO2 in the atmosphere. So that continued until 1930s or so, when all of a sudden along came quantum physics. And quantum physics sort of put the death knell to the greenhouse effect, because what quantum physics was saying was that a photon of light would be absorbed. It would excite the electron in a particular shell orbit of the molecule, but then in order to get rid of the energy, this excited energy, it had to emit the same amount of energy. It couldn't break it down. If it could break it down into two theoretical shorter wavelengths, longer wavelengths of light, but they would have to be an exact match for the one photon that was absorbed. This is a very unlikely process, especially for molecules, singular molecules that are absorbing a particular wavelength of light. So what happens is light's absorbed by CO2 molecule, it gets excited and it bounces around, and then it gets rid of the photon, and it stops bouncing around. It doesn't add kinetic energy to the molecule of CO2, except in a very particular situation where if the electron is vibrating outwards and it connects with another molecule at the same time as it happens to vibrate out, it can give that amount of energy to the other molecule. This is a very unlikely event in the case of a gas molecule. However, if you have a roll of hot black tar on your roof in the summertime, that stuff sucks in photons, it heats up the adjacent molecules, and they're bouncing around and they soften. The tar actually gets softer because the kinetic energy, the photons are being converted to kinetic energy that can actually be translated into kinetic energy of the molecules. So all in all, there is this issue of how effective the greenhouse effect really is. So by the 1930s, it had been pretty much dismissed by all of the scientists. And that was the way things were until Dr. Roger Revelle, who was a pretty well-respected marine biologist, was noticing that the amount of CO2 in the oceans was going up, and the amount of CO2 in the atmosphere was going up, and there appeared to be a warming trend in the atmosphere itself. And he put the two together, came up with this correlation between the levels of CO2 that's going into the atmosphere and the warming. But he, like Arrhenius, didn't do any further research and just basically put it down to, oh, it's just a greenhouse effect. The radiation is being absorbed and it's being transferred to the air molecules because of the level of CO2. He didn't make any correlation between the energy that was being put into the atmosphere by the combustion of the of the hydrocarbons to make CO2. And that is where the essence of the science has started to fail. Funny, in the 1970s, the atmosphere seemed to be cooling. And there were all kinds of reports about a new ice age happening, the potential of a new ice age. This went on for pretty much the full decade of 1970 to 79. Then guess what? The atmosphere temperature seemed to be returning to normal. And once again, along comes the greenhouse effect and the heating. And people started to really take it seriously that there was this greenhouse effect without doing any of the background science that may have said it was something else. So you continue with this kind of situation until you get to the point we have today. Now, I need to give you a little bit of history of science. It's been 296 years since the mercury thermometer was invented. And everyone here knows his name, at least his last name. Gabriel Fahrenheit invented the mercury thermometer in 1714. And that was one of the, it may have been the most important scientific instrument ever invented, because it allowed the understanding of energy, transfer of energy, kinetic energy, and how all energy was related to one another. The development of the idea of kinetic energy and the theories of it is based in the study of thermodynamics, which is thermo is heat, dynamics is movement. So how does heat move back and forth? So the first law of thermodynamics is one that we've all heard before. Energy cannot be created nor destroyed. And that's the way it is. No ifs, ands, or buts. No one's ever been able to create it. No one's ever been able to destroy it. The second law says that heat always moves from a hot object to a cold one. So you put your hand in cold water, you feel the cold. Put your hand in hot water, the heat from the hot water is coming into your hand, just as the heat from your hand is going into the cold water. Your feeling is a differential, but that's the way energy flows. So we have this aspect of what is the essence, the use of energy, and where it's going and what it's doing. And that's what we need to come to grips with. The idea of temperature is that it is a way of measuring the kinetic energy of an object. You stick a thermometer under your tongue and it reads 98.6 degrees Fahrenheit. That allows the doctor to know that you're in what's considered the normal range of kinetic energy in your body, and that you're healthy. If your body starts to over-metabolize, you'll get a fever, and your body temperature will go up. That means you're sick. These are the kinds of things that we know about kinetic energy and temperature. We know that if we're adding energy to a pot of water, it will boil even if you watch it. I have proven it. I know that you can watch a pot of water and it will boil. It takes a while. It seems to take forever, but it does happen. The whole idea is that the energy goes in, it agitates the molecules, makes them vibrate faster, and eventually they turn into gas, and the gas bubbles boil off. And that's what energy is. It's when you're taking a thermometer or any device that measures temperature, whether it's a diode or an electrode or a thermocouple, it's measuring kinetic energy of an object. And that is the essence of what we need to understand about the climate. The kinetic energy of the climate, the kinetic energy of the science of how the climate works. Now, they talk, the IPCC, the International Panel on Climate Change, great acronym for my friend who's talking about acronyms, is concerned with what's happening with the atmosphere. And they should be. They're an international panel. They're supported by the UN. They get lots of money for understanding and talking about this stuff. The thing about it is that they ought to be doing the science properly. Now, they claim that the temperature of the atmosphere has gone up by 0.78 degrees Celsius since 1800. And that they've estimated that number to within 0.026 degrees Celsius. So it's 0.78 plus or minus 0.26 degrees is the temperature rise of the atmosphere. Now, that sounds like they know what they're doing. It sounds plausible that they could do this. Well, let me give you an example about the atmosphere. It's 17 billion cubic kilometers. It has a density that's about 1.3 kilograms per cubic meter at sea level to about, a tenth of a gram at 100 miles altitude. It has a mass of 5.136 times 10 to the 18th kilograms. Now, if you believe that anybody has any way of calculating the absolute kinetic energy to within several degrees Celsius of a mass that size, you should be out somewhere else and not listening to this lecture, because you don't understand the impossibility of what the scientists are trying to convince us they can do. There's no way anybody could measure to within that precision and accuracy the kinetic energy of the atmospheric mass for today, for yesterday, for tomorrow, for last year, let alone 210 years ago, when 50% of the Earth's surface, or more than 50% because the oceans make up 70%, the land mass, 50% of the land mass wasn't even discovered. Antarctica wasn't even known in 1800. The North America was being populated, but very only in certain areas. The northern climate of Canada and Siberia were largely unexplored. And yet they try and tell us that we can tell you what the temperature was back then to within 0.26 degrees, or actually 0.13 degrees, because you take half of the error and it applies to both ends of the scale. It's nonsense. They'd be lucky if they could get within 5 degrees Celsius of an estimate, a real estimate of what the temperature actually is today or any time, because of the sheer massiveness of the atmosphere and the distribution. These numbers are, I'm not making these up. You look them up, you can find them anywhere. And because of that, if you'd say that temperature is a measure of kinetic energy, and we can somehow measure the temperature and get the kinetic energy, if you say it's within 5%, well, the temperature of the average temperature of the Earth is somewhere around 210, 212 degrees Celsius. 5% of that is, 10 degrees. So we can't measure, we can't estimate the temperature of the Earth's atmosphere within that era. And yet the IPCC claims that we can and that we should be worried about it. Well, that's one thing. We should be worried about it, but not because of what they're saying. Now, interestingly, I'm to point 12 already. Combustion facts. All of the climate scientists, the climatologists, everybody that works in science. They seem to have missed the point.